All right, let's do these last set of notes for this unit, looking at centripetal force and Hooke's law. I did make this video earlier, however I found out, or thanks to a student actually, that I made an algebra mistake. Classic problem with making videos at 1 o'clock in the morning. What I'm going to hope though is that with my calculator nearby, I'm not going to make some of the same mistakes. In any case, we are moving forward. Okay. Let's talk about acceleration. Well, what is acceleration? Acceleration is the change in velocity over time. So I'm gonna go back in here. I'm gonna take a little pause with everything else on the screen and say acceleration is change in velocity over time. Now, the one thing I kind of hadn't really talked about is the difference between linear and centripetal acceleration. So this was linear acceleration. So we're looking at if something only accelerated up or down, left or right, it was only in the xy plane. Well, what if something is accelerating on a curve? Well, then that's what we get this called a centripetal acceleration. And so what does centripetal mean? Centripetal literally means center seeking, meaning this object is always going to be seeking towards its center. So if I have, let's say, a little small block, I've got a little block down here, and I was spinning it around in a circle, what direction would that velocity be going? So let's go here and let's look at the bottom. We see that the velocity here is tangential, or meaning tangent to the circle. It is a perfect 90 degrees towards the center. Well, once we rotate it just a little bit, we see now that this velocity is up, and then the velocity is towards the left, and then down. Well, what's going on here is that as the object is rotating around the circle, it is always accelerating towards the center. Regardless of wherever we look at it, it is always curving towards the center. So then we denote this as centripetal acceleration or center seeking. Regardless of wherever I look at, the acceleration is towards that center point. Well, how do we calculate it? We could spend some time deriving the formula for it, but I'm going to leave that for never in this class. We're just going to say centripetal acceleration is velocity squared over r. Well, how do we unpack this a little bit? Well, if you know the velocity or the tangential velocity, so I'm going to say v sub c for centripetal velocity, and you know how far you are from the center, so we'll call that your radius r, you can figure out the centripetal acceleration pretty easily. I am going to add a little bit to this. So the way we did with connecting using Newton's second law, connecting mass with acceleration, F net equals ma, you can do the same thing with centripetal acceleration. That centripetal acceleration equals mass times centripetal acceleration. So centripetal force equals mass times acceleration. We can expand this a little bit, and instead of writing a sub c like up here, we can actually plug in and replace all those variables together. Now you are going to be using this formula quite a bit, so I'd recommend you write it down in notes, have it clear and easy access to it. This one is up on the wall. I do need to make another poster, so but kind of have both these ready when you need to. In the same way, and I'm going to kind of talk about this real quick, is that in the same way that we don't draw F net on any of our free body diagrams, we're also not going to draw centripetal force. You just don't draw it on the free body diagram. In the same way you don't draw F net, you don't draw centripetal force. There are things that are going to cause that centripetal force, but we're kind of like scratching the surface on it, and we're really not going to go too deep. So let's apply this to a situation. We'll say if I had a block on a string and I was swinging it in a vertical direction, so kind of up and down. Draw all the forces on the block and calculate the centripetal force on the block. Well, the very first thing I always tell you to do is to draw weight. So at the block, when it's at the bottom, weight is always going to be pointed downwards because the gravity will not change. What other forces do we have going on there? Well, since we have a rope pulling inwards, we're going to call that tension. But notice tension changes the direction and what it's pulling based upon where it's at. So at the bottom of the circle, it's pulling up. When you're on the left or right, pulling inwards, and the top pulling down. And so that's what we're going to call all of the forces on the block. Notice we did not draw a centripetal force, but we can calculate for it. So let's do that. So centripetal force equals mass times centripetal acceleration, or we could use that equation kind of wrote earlier, mv squared over r. So centripetal force equals 5 times 3 squared over 0.75. I believe this is going to be 60 newtons, but I'm just going to double check because I did make this video before and I did make an algebra mistake. It's just my fault there. So 3 squared, 5 times 3 squared, divided by 0.75. Yep, 60 newtons. Just wanted to double check. Cool, and that is it. We drew our forces. We have centripetal force, F sub c, and it's 60 newtons. So in total, the net force on this object is 60 newtons, and that's what's causing it to accelerate inwards. Okay. What happens then if I were to take this and instead of rotating it vertically, what if I were to rotate it horizontally? And hopefully, maybe if you get to the point in the class where you get to do some of these little, I'm gonna call them bonus labs, where you get to actually create this device right here. So this device is gonna be a PVC pipe. You're gonna rotate kind of like a helicopter blade, a pendulum bob above your head, and that tension you create, that centripetal force, is going to create enough tension in the string where you should be able to lift a heavy object. I think it's really, really fun. If you get to it, fantastic. If not, I'm not too concerned because we're kind of only scratching the surface on this homework or on this unit. So let's read the question and see what we got. So we got a 0.5 kilogram block swinging in a circle, velocity of 2. Tension is 15 newtons. How long is the string? So we're looking for the radius here. We don't know the radius. We do know all of our other pieces of information. So I'm going to go back to my question from earlier. We got centripetal force equals 15 newtons. Our mass is 0.5. And velocity is 2 meters per second. Ooh, let's put in all of our units. Kilograms, 2 meters per second squared all over r. Now, I actually did this a little bit of an intentionality just to show you that the units should cancel out to meters. So one thing I really haven't talked about before is what is the definition of a Newton? And that's kilogram meters per second squared. So that's how much it would take to lift 1 kilogram, a meter, in a specific time interval of a second. That is the definition of a Newton. It's just a standard number we use to reference it. And so what we do here actually is we can plug this in right here. So let's put 15 kilogram meters per second squared equals 2 squared is 4. Half of 4 is 2. Kilogram meters squared per second squared all over r. And so what we find out is kilograms cancels out, second squareds cancel out, 1 meter on the left side cancels out 1 meter on the right side. And so I'm left with just the units of meters. Does that make sense? Well, yeah, we measure the distance of our string in meters, so all the units will cancel out to what we're looking for. But I digress. I'm just going to go back to, and we're going to strip all the units away and just look at the numbers. So 15 equals 2 over r. Multiply both sides by r. 15r equals 2. Divide both sides by 15. This is what I did earlier. As far as my mistake, I did 15 divided by 2. Anyways, 2 divided by 15, we get 0.13 meters, which is about 13 centimeters, and it sounds about right. Okay. If you get to the point of doing this in the lab, I think it'd be super awesome if you get to. If not, that's okay. But we should be able to solve for some centripetal acceleration questions. Okay. Let's move forward. So we talked about centripetal accelerations, one of the unique forces we're going to talk about. Now let's talk about Hooke's law. Hooke's law is the forces in springs. Now I am going to say there is one small little caveat before we begin any of this, is that technically Hooke's law, Fs equals negative kx. I am not going to be particular on the direction of forces, because of it's a frame of reference question. So if you look up Hooke's law, you'll kind of see two versions of this formula. One's positive, one's negative. What I'm going to say is that for the sake of this class, we're just going to use the force of a spring equals kx. And with that, we're not going to worry about our frame of reference questions. Okay? So that being said, let's actually move on to it. Let's erase all that. Let's go away. Now, Hooke's law, what is it? Well, if you're doing anything fancy in science and you get to name yourself after it, you can talk about this. Hooke's law is the force in a spring is based upon how far you stretch it and the stiffness of the spring. So it makes sense if I have a spring that's really stiff, it would take more force to pull it. And if I pull a spring really, really far, it would take more force to pull it. Okay, so let's look at it. Well, we got a picture right here of an unstretched spring. And I want you to notice is that this x value right here is your stretch length, not how long the spring is. And so let's say an unstretched spring length of, let's say, 1 meter. If this whole thing now is, let's say, 1.25 meters in length, then my x is going to only be 0.25 meters. Okay? When you're looking at stretch distance, you're not looking at how long the spring is, you're looking at how far you've stretched it. And we're going to practice that here in a moment. Okay? The only thing kind of different is, well, force of a spring, we'll measure all forces in newtons. K is a new thing. We're going to call that our spring constant. It is an ideal strength of the spring, and that's going to be in newtons per meter. And then x, which is distance, is still going to be in meters. You will have to be a little cautious here that the spring constant's in newtons per meter, but some of our questions actually have it in centimeters. So be really cognizant. 100 centimeters equals 1 meter. If you don't remember how to convert, you can kind of pull me off the side. Hey, Mr. Williams, help me out. If you don't need help, and conversions is your jam, cool. Moving on. All right. So let's look at this question in general. Okay. A load of 50 newtons is attached to a spring hanging vertically, stretches the spring 0.05 meters. So let's draw a picture. So we got a spring hanging vertically, and it caused, let's see if I can draw the same spring. There we go. Try to do at least. There we go. Is that whatever our stretch distance was, is 0.05. I'll get a little squish there. Let me erase that. X equals 0.05 meters. That's how far my spring was stretched. Well, what do I know? I know Fs equals Kx. So the force we put on the spring, which is a weight of 50 newtons, a load of 50 newtons, so 50 equals K times 0.05. Divide both sides by 0.05, we get a K value of 1,000 newtons per meter. So this tells me my spring takes 1,000 newtons to stretch it a full meter. Now we're not going to be stretching our springs that far. We're going to be just a couple of centimeters, nothing too terribly long. But I digress. Just to double check, I'm in the middle. There we go, 1,000. Okay. Like I said, I did make an algebra mistake before, and I apologize for that. But I just want to double check all my algebra's good. Alright, let's try this out. I now take the spring and I place it horizontally on the table. But my stretch distance, how far I stretched it, is X is going to be 0.11 meters. What is the force required to now stretch at this distance? Well, we're going to go back to Hooke's law, Fs equals Kx. The force on the spring is what we're looking for. The spring constant stays the same. And our stretch distance 0.05. So the force we put on the spring is going to be, my brain. Oh, I made a mistake. I was trying to do too many things at once. My bad, folks. My stretch distance isn't 0.05. It's 0.11. There we go. That's going to be 110 newtons. I was like, I thought it should be 110. Almost made a mistake again. Have to restart this whole video over again. 1,000 times 0.11. Okay, we get 110 newtons as our answer. So let's rewind a little bit. Let's talk about what's happening in here. So we took a spring, we are hanging horizontally. We found how stiff the spring was. We then laid it vertically and figured out how hard we had to pull it, how much force we had to pull it with in order to go a certain distance. When it comes to Hooke's law, this is pretty much what we're doing. We're given two of these variables, you find the third. Boom, done, moving on. However, in lab, we are going to graph Hooke's law, because what happens if I take the springs, and now let's say I've got one spring. What happens if I put them, if I had an identical spring? Well, let's say Control Z real quick. What's happen if I had an identical spring and I hang them parallel to each other? What does that do to my K value? So let's say K value by itself is 100. What would my K value be if I put them in parallel? And what would it be if I put it in series? How would that affect my effective spring constant? Now you might say, well, Mr. Williams, spring constant is a constant. It's a constant after all. True. The spring constant of the spring itself doesn't change. However, how it works effectively is changed. Think about a trampoline. If we're looking kind of the bird's eye view on a trampoline, you have tons of springs all working inwards. Now, if we had just one of these springs, there's no way only one spring could hold your body weight. So what do? Is we put a bunch of them in parallel to each other. So this is parallel. Oh. Come on, Mr. Williams, let's spell parallel right. Parallel. And this one is in series. how does that change your effective K value? Well, that's what your lab is going to be on and what you're going to see. I'm going to erase this real quick. And let's draw a picture. So if we were to graph the force on a spring and its stretched distance, we would find that the line of best fit would be our spring constant. Well, how does it change based upon if it's put in series or parallel? And so one of them, your K value is going to increase, and on the other one, your K value is going to decrease. And that's what you're going to try to find out and solve for your lab. I'm not going to ruin the surprise for you. Okay? If you have any questions about this, about centripetal force, about Hooke's law, welcome to pull me off the side. I'd love to help you out. But it's officially in your hands, and I'll see you in class. Take care.